Ethereum faces a hard challenge, scaling to millions of users without sacrificing security or privacy. In this course, we'll make ZK-Rollups understandable, separate scaling from privacy, and build a practical lens for evaluating real-world ZK products. We'll start with blockchain and Ethereum fundamentals, then move into ZK-Rollups, privacy, and product strategy. Plan for about 6 to 10 hours, depending on how deeply you explore the examples and research. The course builds from cause to consequence. First, we examine Ethereum's scaling pressure, congestion, high fees, limited throughput, and poor user experience. That pressure motivates rollups, and then zero-knowledge proofs as a way to scale while preserving core security assumptions. Once the mechanics are clear, we'll turn to harder questions around privacy, compliance, adoption, and product trade-offs. By the end, you should be able to evaluate ZK systems strategically, not just describe how they work. Use this course based on where you are starting from. If you are new, move in order and resist skipping the foundations. If you already have experience, treat the modules as gap fillers, especially around architecture, privacy assumptions, and trade-offs. If you are advanced, use the course as an evaluation framework for products, protocols, and markets. In every case, take notes, revisit diagrams, and pause when something feels unclear. That is where learning compounds. Here's the key tension. Public blockchains give us security and decentralization, but every system has limits. Once demand exceeds capacity, users feel it through congestion, higher fees, slower transactions, and delayed finality. Think of a blockchain like a highway with a fixed number of lanes. When only a few cars are driving, traffic moves smoothly. But during a spike in demand, the lanes do not automatically expand. Transactions compete for the same limited block space, so users pay higher fees, wait longer, or see transactions fail. Scaling means adding more useful throughput without giving up the trust and security that make the network valuable. The trilemma is a useful way to think about blockchain design. Decentralization means many independent people can run, verify, and challenge the system. Security means attackers cannot easily rewrite history or push invalid changes. Scalability means the network can serve many users at low cost. The hard part is that improving one side can strain another. So scaling is not just about speed. It is about adding capacity while preserving trustlessness and resilience. Block space is scarce because each block can only carry so much data, while demand can be much larger. Bigger blocks may seem like the obvious answer, but they shift costs onto validators. Validators need more bandwidth, storage, and computing power to keep up. As those requirements rise, fewer people can validate independently, which weakens decentralization. For that reason, block space remains limited by design, and users compete for it through transaction fees. Gas is Ethereum's way of pricing the work a transaction asks the network to do. Because block space is limited, demand spikes create bidding pressure. Users who want faster inclusion pay more, and average fees rise. This is most visible during NFT mints, heavy DeFi trading, market volatility, or major launches. If fees climb too far, small users and low-value transactions may simply be priced out. This fee pressure has real product consequences. Validators cannot include every transaction immediately, so fees become a priority signal. Higher bids move faster, while lower bids may wait, fail, or get dropped. A normal $3 confirmation can become an $80 surprise. For applications, that unpredictability can break onboarding, reduce retention, and make the product feel unreliable. Three terms are especially important when we talk about scaling. Throughput is capacity, how many transactions the network can process over time. Latency is waiting time, how quickly a user gets a response. Finality is settlement confidence, when a transaction is effectively irreversible. Different applications weigh these differently, depending on what users need most. Scaling limits become real at the moment a user tries to act. Imagine someone minting a $20 NFT, then seeing a $45 gas fee. They may wait, switch networks, or leave entirely. Slow confirmations create a similar problem. Confidence drops because the outcome feels uncertain. So scaling is not just throughput, it is product experience. Teams must design for predictable cost, fast feedback, and reliable completion. One tempting fix is to make blocks bigger, because larger blocks can carry more transactions. But that extra capacity is not free. It requires faster connections, stronger machines, and more storage from every validator. If fewer people can afford to run nodes, verification shifts toward large operators, and the network becomes easier to influence or disrupt. The goal, then, is not simply more transactions per block. It is more capacity while preserving decentralization and independent verification. That is where Layer 2 systems come in. Scaling is not just about making transactions cheaper. It is about increasing usable capacity without giving up Ethereum's security. Layer 2s move most execution off the main chain, where activity can be processed faster and at lower cost. Then they post data, proofs, or results back to Ethereum, so Ethereum remains the anchor for settlement and security. That basic pattern is what rollups build on. The core lesson is simple. Ethereum is valuable because it prioritizes security and decentralization, but block space is scarce. As demand rises, congestion, fees, latency, and finality all matter. Scaling means managing those trade-offs, not ignoring them. Next, we'll see how Ethereum becomes a settlement layer for execution elsewhere.